Good afternoon. My name is Oliver Style. I'm going to present EnerPHit, simple solutions for air tightness in rehabilitation projects. The EnerPHit standard offers a seal of quality for the renovation of existing buildings. It also offers transparency in the real estate market, and through a holistic approach, it also establishes a safe roadmap for undertaking an energy rehabilitation project, with the possibility of repeating a step-by-step or staggered reform with a correct combination of improvements that would avoid potential humidity problems. This can also facilitate financing, since the required investment for a complete rehabilitation is logically important. The EnerPHit standard offers two ways to obtain certification, based on demands or components. The demand-based approach focuses on performance, on features similar to the requirements for passive house in new buildings, whereas the components-based approach is prescriptive. In other words, the different constructive elements must comply with maximum thermal transmittant limits. Solar load must be reduced to avoid overheating problems. And then there are a series of common requirements for both approaches, including airtightness as a requirement. A final value must be achieved in the blower door test of less than 1 renewal per hour, 50 pascals. This may instill fear in technicians, but it is a challenge in rehabilitation that can be achieved. So what infiltration levels do we have in buildings? In new passive house buildings, under rehabilitation, we have infiltration levels of 0.6, and in the case of rehabilitation, in this case, 1 renewal per hour, a new technical code for high capacity buildings, well, the requirement is less than 3 renewals, increasing to 6 renewals in the case of not very compact buildings. And in existing buildings, although obviously this varies enormously, we can typically find values of 10 renewals per hour, N50. When rehabilitating existing buildings under the passive house standard, we're talking about a reduction by a factor of 10 at infiltration level, something which is clearly a challenge. Rehabilitation clearly has its complications in that sense. So it's essential that we find economically and technically viable solutions to be able to undertake this part of the project and the construction work, and thus reduce infiltrations. It is also essential when implementing these kind of improvements or undertaking such rehabilitation work that we reduce infiltrations and logically control air renewal with a dual-flow heat recovery system. Okay, so now let's look at how infiltrations occur in a normal building. Let's look at the thermodynamic processes which cause air infiltration and exfiltration. Wind pressure on the one hand, from the facade, on which the wind induces air infiltration and exfiltration on the opposite side. So this becomes especially important in tall buildings. We must also mention the chimney effect. In a building or home heated in winter, warm air rises, causing exfiltration on upper floors and therefore infiltration on the lower floors. This can potentially be dangerous in areas where there is radon gas. I'll explain an example later on. And then combustion and ventilation. Balanced non-double exhaust ventilation flow, where a combustion unit, boiler or stove, requires air for combustion, and this causes infiltration, just like kitchen hoods or fans in bathrooms once they are activated. The airflow that these fans have to extract has to come in somewhere, so it enters through cracks or fissures in the building. And in passive house, we practically eliminate these infiltrations. And the reduction in these infiltrations offer many advantages at energy, economic and comfort level. Lower heating costs, lower cooling costs, albeit not to the same degree, and also advantages in terms of health. Let's look at an example of the measurement of radon gas concentrations in a study carried out by Barry McCarron and other experts, which will be presented later as part of this conference. They measured the concentration of radon gas in a total sample of 122 dwellings, 25 reference homes, 97 passive house certified homes, of which 5 were homes certified under the EnerPHit standard. In other words, the infiltration levels in passive house buildings were between 0.6 and 1 renewal per hour N50. The graph shows the results of average radon concentrations in the passive house homes, on the ground floor and on the first floor. And we can observe that the average concentration was below 40 becquerels per cubic meter, with minimal variation between the ground and first floors. However, in the reference homes, radon concentration on the ground floor exceeded the recommended limit of the WHO of 50 becquerels per cubic meter. And then on the first floor, the concentration was lower. The difference between the ground and first floors in the reference homes was due to the phenomenon we mentioned on the previous slide, namely the chimney effect. When the home is heated in winter, hot air rises, there is exfiltration on the upper floor and infiltration on the ground floor, causing radon to enter. Well, this is just one example of one of the advantages of being able to control and reduce air infiltration in a passive house home, and logically control air renewal mechanically with heat recovery. The project I would like to present was carried out in the city of Barcelona, in Pedralbes district. Here you can see the companies that participated in the project. The building was built in 1954 for residential use. It has a constructed area of 2,050 square meters, distributed into a basement, ground floor, and 3 floors above ground with 4 new homes. Part of the ground floor is in contact with ground level, and the facade comprises double-row manual brick, 29 centimeters, with artificial stone blocks on the north and south facades, and part of the more elongated facades from east to west, where the facing brickwork is visible, as shown before. The floors and roofing were made of precast concrete joists, reinforced at the beginning of rehabilitation, as evident in the photograph, with ceramic vaults and 3-centimeter terrazzo flooring. So, on the inner face of the facade walls, plaster and tiles were removed, depending on the location, to leave it exposed from the inside. The components approach was adopted, among other things because we couldn't insulate from the outside, from the exterior. A dynamic thermal cycle analysis was performed, which I will describe later. placing very thick insulation on the interior of these solid brick walls exposed to the rain, because this could potentially cause problems of damp, something which I will also explain in detail later. So the useful life of the components in that sense was better suited to the project's needs. In any case, the airtightness requirement was always the same, a renewal of N50. The ceiling or hermetic layer was designed as follows. Staircases and elevator openings were incorporated into the hermetic or airtight layer in order to seal the entire building. However, a hermetic layer was also established by floor and property. This was done for two reasons. Firstly, to facilitate airtightness pre-tests using a single blower door machine per floor. That is, as the different spaces were all sealed between floors, we could test each floor, provisionally closing entry doors, etc., to be able to detect, correct, and identify infiltrations on each floor. And the second reason was also to improve acoustic comfort of the homes, sealing, as I said before, the different points of transition from one floor to another, staircases, etc., thus eliminating the transmission area. And also, to a certain extent, heat gain or loss that could occur between one property and another, according to temperature conditions and set point conditions between each property. So first, to determine which material we were going to use for the air barrier, a series of hydrothermal dynamic simulations were performed with a WFI tool to check the risk of moisture damage with different air barriers. A permeable or breathable air vapor barrier with an SD of 0 to 3, a moisture barrier, SD of 2 to 50 meters, a vapor barrier 50 to 100, and also variable diffusion panels, normally 0.3 to 25 meters. So through this analysis, we were able to identify these solutions that offered greater security and certainty regarding protection against humidity damage, which is always delicate when insulating internally on the interior in solid walls exposed to rain. So I would now like to present the results of three different solutions. One was simple plaster-based solution. Here we can see a simulation performed over 10 years, analyzing relative humidity on the cold face of the insulation on the inner face of the wall. In case 2, plastering, indicated by the blue line, well, a water-repellent treatment was added to the outer face of the brickwork, and an improvement was obtained insofar as relative humidity peaks fell below 80. And then finally, we compared this with the incorporation of a moisture barrier on the interior. This indicated that when compared with solution 2, hydrothermal performance worsened to a certain extent as relative humidity increased on the cold face of the insulation. So we decided that the solution to choose was plaster as an air barrier, permeable to vapor, combined with water-repellent treatment on the exterior, as shown in the photograph. We can see that the effect of this treatment confers the brick with certain properties as if it was a fabric with Gore-Tex treatment that reduces or eliminates water ingress in liquid form, which may potentially penetrate the interior. Clearly, this type of treatment has a durability of a certain number of years that will depend on climatological conditions. However, in my opinion, this is an interesting solution, because if the period of activity or efficiency may be, let's say, 5, 6 or 7 years, well, at least this will cover the first part of the work, in which all of the work is drying. and thus it will confer a certain degree of protection. In this case, for walls that are exposed to rain, always bearing in mind that there are two sources of humidity from the exterior, rain, wind, and on the interior, humidity generated or moisture generated by people when performing their activities. So the solution chosen was plaster on walls, partitions, ceilings and roofing, a simple solution which was well known to the technicians, and basically this gave us a solution to achieve airtightness in these elements. On the flooring, we opted for a liquid membrane. Here we can see the construction details. On the first drawing, we can see the ground floor and sanitary formwork or flooring. The liquid membrane conferred airtightness at ground level, and then on the vertical partitions, well, 10 millimeters to 1 centimeter approximately of plaster. Cellulose insulation was projected on the walls on galvanized steel profile uprights. The profiles were slightly separated from the wall to avoid creating a thermal bridge, and with double plaster board finishing before applying finishing in the installations, and then a cellular glass insulation was laid on the flooring. The materials were chosen based on environmental impact criteria, because the building was also certified for that purpose. This slide shows other construction drawings. Plaster was also used in roofing. This photograph shows before and after. The picture is self-explanatory, showing plaster finish, covering the entire interior face of the facade walls, the sunblind or shutter boxes, and ceiling and roofing vaults. The openings from one space to the next opened in the partition walls were also sealed to eliminate the risk of exfiltration from the building through those partitions. This is also a characteristic of rehabilitation projects. It's important to ensure continuity in the hermetic or ceiling level for all interior partitions. Openings from one floor to the next were sealed with plaster and then brush painted with polymeric hermetic paint. This slide shows liquid membrane applied on the flooring. Given the results, we could possibly have done without this membrane on intermediate floors. However, this is a solution that can be applied quickly, and it was later protected with a mortar compression layer to be able to continue with the work. Windows. Well, windows are always a weak and critical point when dealing with infiltrations. A window frame system selected comprised windows integrated with shutter boxes, factory-made, and in conversations with the window installation company, a system and construction details were agreed. This allowed a solution that works very well. The first step in window installation consisted in the laying of tape around the entire perimeter of the window and the shutter box prior to placing the fixing brackets made from stainless steel. And this allowed the hermetic tape to pass inside the brackets as seen in the image in the center. The windows were placed on the insulation layer inversely to the normal procedure used with the SATE system, thus reducing the installation thermal bridge. And here we can see the final result. Well, in my opinion, this is an interesting solution for rehabilitation projects, but also for new buildings, new constructions. But above all, using windows with incorporated or integrated shutter boxes makes it much easier to complete the work and ensure airtightness. Blower door tests were performed, 2 operators hanging outside with a smoke plume. The right-hand photograph seems to give the idea that there was quite a lot of smoke, but in reality there was very little infiltration, as shown with the results of the blower door tests: 0.36 renewals per hour, 50 pascals, 0.31 on the second floor, and 0.47 on the third floor. The impact of these infiltrations on energy consumption, calculated with PHPP, are shown in the following graph. Compared to a level of infiltration of 10 renewals per hour, consumption, not demand, consumption, taking into account the performance of the installations, was reduced by 37%, according to these calculations. In euro terms, for the entire building, that translates to about 9,255 euros per year. It should be borne in mind that this was Barcelona, which has a mild climate, so savings would be even greater in buildings in more continental climates in the centre of the Iberian Peninsula. And with that, I would like to end and thank you for your attention.